Okay, hello everyone. Welcome back to the Audio Arena. I hope most of you had an interesting, exciting summer vacation and somehow managed to get finish your IQ submissions. It's my great pleasure to introduce our today's speaker, Luigi Acerbi, who is currently a professor at the Department of Computer Science at the University of Helsinki. And prior to that, he was did several postdocs, one in Geneva and the other one at NYU. And prior to that, he obtained his PhD at for computational neuroscience in Edinburgh. So with that, thanks for coming today, Luigi, and floor is yours.
Thanks a lot for inviting me. And yeah, it's very exciting to talk to this community, the AutoML community. And I think we have a lot of interest in common coming more from the Bayesian probabilistic modeling side. And in this talk, Accelerating Bayesian Inference and Data Acquisition via Amortization, I'm going to present essentially two papers of ours. And one was presented earlier this year at AStats. And this one was actually just accepted at NeurIPS this year as a spotlight. And so these are all the collaborators without which these works wouldn't exist. And one in particular I want to thank in advance, and it's Dowland, who's first co-author of the first paper and also first author of the second paper I'm going to present. And essentially these slides would not exist without him. So thanks Dowland for preparing this. And all right, so let's get into it. So what's the general idea here is that we need both data acquisition and inference. And the problem is that essentially the problem of data acquisition is, okay, so how do we select the data which are most informative for the task we want to perform? And then let's say problems. And the problem of statistical inference is that once we have this data, okay, what do this data tell us? Let's say what's the outcome? What are the conclusions that we can draw? And examples come from medicine, material discovery. Famously, there are lots of applications in human-computer interaction and so forth, and so on and so forth. And so the first question is, okay, so how do we select data which are, let's say, most informative for the task at hand? And well, we have an answer, and this answer has been developed in many years, let's say in the past decades, and it's called Bayesian experimental design. And the idea is that to mathematically guide experimental design, let's say where we placed our next observation, our next experiment, in such a way that it reduces uncertainty about the parameters, quantified, for example, via the entropy of these parameters. And this can be phrased mathematically as maximizing the expected information gain about the parameters. And so this is beautiful and elegant, but like many things in Bayesian inference or Bayesian experimental design, everything is very slow to compute. And similarly, let's say, so we have a very nice framework for statistical inference. So once we have the data, how do we make inferences about what this data tell us? And well, Bayesian inference tells us how to do it. You can update your belief about the parameters, represent it as a probability distributions, and then compute its value through Bayes rule. This again is all very nice and elegant, but computing it in practice is quite expensive. And you can use MCMC, variational inference, but that these are all kind of costly. All right. So, and the point is, there are many situations in which we need to be fast. Now we're being a bit dramatic. We say every second is critical, but let's say, even, some situations, let's say still we cannot spend all this computation to get the data and then do inference. So we need to rapidly decide, which data points we need to connect. We need to rapidly learn what to do with this data. And again, some examples, let's say, let's say a bit glamorous, let's say disaster search and rescue. Let's say we would need to rapidly decide, let's say, where to do our searches. Okay? And then, let's say, based on the results of the searches, we need to decide where to move on next or what to do next, say, take some decisions for, deploying and intervene. And let's say, maybe also more common for some of the applications that we actually do is medical diagnostics. So let's say, so you can kind of query or find, let's say, experiments in the medical literature or actually perform these experiments. And then let's say you can use this information you acquired after experiments, let's say after these measurements, to diagnose or decide, let's say, what to do next. And so the solution, so one solution that we, the field has been proposing in the past years is amortization. And the idea is that, so if you, can you see my mouse and the cursor?
Yes, yes, we can.
Great. So without amortization, the idea is that every time you get new data, at deployment, you need to reperform this costly computation, whether it's inference, experimental design. So all of these, are redone from scratch every single time. So the difference is that with amortization, also known as pre-training, effectively. So what you do is you pre-train a big machine learning model, also often a neural network, and you pay the cost for training initially, and this can be quite expensive. But then at deployment time, let's say this network during training has learned a mapping from problem to solution. And then at runtime, you can just see the problem and immediately, with a forward pass, you get a solution for that specific problem. So, and that's, eventually the cost is amortized in the sense that, at runtime, you only pay, just the cost of a, forward pass of your network, although you spent a lot to train it. And so now this essentially kind of gives us a nice solution. Sorry, this got stuck. That while for traditional Bayesian experimental design, BED, trying to find what experiments to run next, so this design what to measure next was expensive, now we can pre-train it offline and do what's called now amortized BED. So we learn a policy network that learns, given a sequence of design and outcomes, what experiment to run next, which design to probe next. And we do that offline. And then at runtime, you can just give it a sequence of past experiments and their outcomes, and it will just kind of give you instantly which experiments you need to run next. And that's, there's a bunch of work in this direction in the past years. And similarly for amortized inference, again, so if you were to run Bayesian inference, there is a long tradition of methods you can use, typically MCMC or others. These are famously, let's say, costly or can take quite a bit of tweaking. But there are these more recent approaches of amortized inference, or for example, neural posterior estimation, where again, you use a neural network to learn a mapping from observed data to a posterior distribution for the parameters that could have generated those data. And it's actually pretty easy to train because you only need to have a simulator. You train the simulator, you train your network on samples from the simulator. These are pairs, parameter data, and then you learn to map data back to posteriors. So, and this again, there is a lot of work in this area in the past few years. So this was to learn parameters, but the other thing we want to predict is data. This is a slight tweak, but let's say in a Bayesian inference, you sometimes care about the parameters, so that's called posterior inference. But sometimes you care about predicting new data. So that's called in Bayesian lingo posterior predictive, in the sense that you want to predict data given past data. And there is a family of methods that actually do that, again, in an amortized manner. They're called conditional neural processes. And then a bunch of other related methods that fall into this family. And just to kind of get into the meat, I will explain a bit what neural processes, and specifically a conditional neural process. And but the idea is, I need to learn how to do this. Okay, this is not going back. Okay, now it's going. All right, sorry. So a neural process is trained in this way. And so I'm going to explain a bit what this is. So the idea is that we have some past data, which is called, say, the context. And then we want to predict at specific points. And these are, let's say, our target points that you want to predict at. Imagine, let's say, a function that like a Gaussian process, you want to predict these functions at a bunch of points, and you want to predict the values of those points. So let's say you can phrase that as a probabilistic prediction. And let's say what this conditional neural process does is kind of the simplest possible thing, which is, okay, I'm going to map the context of previously observed points and to a neural network. And then I'm going to use that to parameterize the prediction, which could be, for example, a Gaussian at the points that you want to query. And this, as you can see, is a product. So these are all independent. And you might say, oh, that's not very strong. But it actually turns out that we can relax this assumption and we can learn to predict also the dependencies in this way. So basically, the key point to learn here is that we just use a neural network to predict new points having seen past points. And how this is done is you have a function that you can simulate synthetic data, or maybe you can just collect a large data set of functions, and you can train on this. How? Well, these are, let's say, the points that you observe as this function. Now, during training, what we do is we divide this training data into two sets. These are training points or context points in black, and target points in red, okay? And we just tell the network to learn to predict the red points from the black points, okay? So we learn to predict the targets given the context, okay? And this is self-supervised because we have all of these points. So we just say, okay, now we kind of hide the red points and you need to predict them. And that's it. And since, we have this, we can just use a kind of standard maximum likelihood training, which is not very stable. And the idea is that, so we just have a lot of these functions that we have a large data set of those, or we can generate a lot of those, like, for example, using Gaussian processes. And here, you can see them. We're just sampling them. There's a lot of different functions that we're learning from. And the idea is that, we can just then learn to predict at test time. And now, this idea is simple, has been expanded in many, many different ways in the past years. And there is a whole zoo of methods that they're either called neural processes or they're very related to the neural process, such as, for example, the PFNs that you're probably familiar with. And so let's say perhaps unsurprisingly, the most powerful models in this class are the ones that use transformers as the backbone to do the prediction. And there are two closely related methods. One is transformer neural processes, and the other one, again, is the PFNs. But I say the underlying logic is very similar, and I can cover it very quickly. The idea is that, again, you have some data points that you split between context and targets. And the context, we know both the input value and the output value. For the target, let's say at training, we only give the input, and the goal is to predict the output value, which we stored on the side. Then we pass through the embedding layers of, say, this can be an MLP or whatever else you want to use as an embedding. And then in the end, you end up with a tokenized representation, an embedding vector. And then essentially you pass through your transformer blocks, multi-head self-attention and cross-attention. And the crucial point is that the context points all speak to each other as a set, because this is a set, the order doesn't matter. And then essentially the targets look at the context set to decide what to do. And because again, you want to predict at the target, so the information flow from the context to the target, because you want to use the context to predict what happens at the targets. And then you do a bunch of blocks of this, and then you do inference, let's say decoding from the targets with whatever you want. You can decode using a Gaussian, so the output here will be the mean and standard deviation of the Gaussian. But you can use fancy stuff like a Riemannian distribution, like the PFN use, which is this kind of bunch of uniform distributions, or say blocks, and then let's say these Gaussian tails, or you can use a mixture of Gaussian. You can use whatever you want here. But the point is that you're making a probabilistic prediction for the values of the targets, and then you get, so during training you get essentially a score for how good your prediction is, and then you can train to get better. Now, these are great, and they predict essentially new data given past data. But there is a point that all of these models in the past only worked with data. So you condition on data to predict new data. And in fact, let's say a lot of the times we care about parameters, which we call, let's say, latent, in the sense that we don't know them and we want to know them. And sometimes we don't know them, we want to predict these parameters. Sometimes we actually have some information about these parameters, we want to be able to use this information. And this was not possible in the past. And what I want to convince is that this seems to be a somewhat maybe obscure or niche, probabilistic inference problem, but it's not. A lot of tasks actually boil down to conditioning on some information you have and predicting something else, which is either data or these latent variables. For example, image completion classification is just, say you might have some data like a partial digit here, and we may or may not have some information about the latent class. In this case, we don't, so it's completely uniform. So when we make our prediction, so for image completion would be try to predict what happens here. And here, we don't know, so we predict a blob. And our prediction over the value of the digit is kind of, this might look like a 3, but could also be a 2 maybe, or maybe a 7. So let's say, so we kind of spread out. So but this would be in classification, that's what you do. But now suppose I know that this value is 3. Now I can do conditional in painting, for example, and I'm generating the 3 because I know that this was supposed to be a free. So these are the same task. It's all again conditioning and predicting. Another famous example is Bayesian optimization. So the idea is that here the data are some observed values from your function, here in a 1D function, and the latent are the location and value of the optimum, of the global optimum. And then, we might want to predict other function values, like, you do with a GP, etc. Or we might want to directly predict the location or value of the optimum, okay? And similarly, again, for simulator-based inference in a probabilistic inference, I might have, a time series and some parameters that govern this time series. I might have some knowledge about this parameter, which is called a prior, and I might want then to make inference based on this prior and this observed data, to kind of, well, in this case, you kind of predict the continuation of this, or the previous time step of this time series, and also get a better idea of the parameters. And this is all the same framework, okay? So these are all different tasks, but this is all conditioning and predict. So now, why I spend so much time doing that? Because now the idea is that, well, hopefully I convince you that this is actually quite a fundamental problem. And if we can solve it, we can do a lot with it. And so what we did in this paper, the one accepted A-stats, well, presented also, is that, well, we can extend previous work on neural processes to also deal with these latent variables. For example, the value and location of the optimum in Bayesian optimization. And what we do is simply we essentially expand the existing space to include both data and latents. And the way in which we do it is literally by adding, for example, to the architecture, the ability to condition not only on data, but also on latents, which once you plug them into the system, they just add their tokens. The beauty of transformers is that everything becomes once it's embedded, it's just this vector, and then you can just talk to the other vectors exactly like everything else, right? So transformers are very natural for this task. And the same thing is that once we have this latent, we can also condition them or predict them. So I say now we can just predict, putting as target one latent, then we get a prediction for this latent value. So for example, this is just some example. We can do image conditioning and prediction. So we are given this lower half as context, so as scene, and then we can condition some of this latent for this data set is celeb A. So we can condition, for example, on the bold latent variable to be true or false, and then we get different image completions. So let's say this is just again a toy example to show that this works. We can do it with functions. So these are traditionally what you will get. So these are observed points, the black dots. These, you get your kind of social plots from our predictions. You can get them from a neural process. These are data predictions, given data. But now we can also predict the location of the optimum here in the blue line, was a blue distribution, or the value of the optimum. And surprisingly, for example, you find that the value of the optimum, the global optimum, is below the currently observed best value. We didn't teach this to the network. We just trained it, and eventually it learned that, yes, the global optimum is likely at this point or below. And then, you can do a lot of stuff with this, but I don't have the time to explain. And I think you can do with ACE is put priors over these latent variables. Remember, we often want to do that. And we find a way to do it simply by essentially vectorize. It's not a particularly clever way. We just discretize it and then plug it into the network, and it works. I don't have much to say. I don't want to kind of spend too much time now on this because I could speak about ACE for another full hour. I wrote a blog post about things you can do, fun things you can do with ACE. For example, you can use it for Bayesian optimization. You can do a lot of stuff. You can go see the paper. But anyway, so what I want to kind of convey is that it's a very, very flexible framework in which you can do a lot of things as long as you can condition and predict on these variables. Now, this was about data, but the other half is all right. So this was about inference in the sense that we can, given data or these latent variables, predict data or latent variables. But these data are given. It's not telling us what to do, how to collect new data. I mean, you can use this in some more complex loop, but let's say it's not, say, the data acquisition part is not amortized. And so we realized that there was this disconnect between amortized Bayesian inference, like ACE, and the existing method in amortized Bayesian experimental design, in the sense these two kind of were progressing completely separately. So as we said before, mentioned before, we want to do both. We want to be able to rapidly collect data and rapidly perform inference. And also, we want to be able to dynamically change the collection strategy, because say what you're going to collect will depend on which kind of information you care about. So I might care about, for example, if you're doing Bayesian optimization, of course, you might care about the location of the optimum, but you might also care about the value. It's not obvious that you care about both. Or sometimes you might only care about the value of the optimum, and you don't really care about the specifics of the location. For example, this is just an example of different things. Other times you actually don't care about the location or value of the optimum. You only care about knowing the, let's say, how many optima there are. So you might have different objectives. And the idea here is that, okay, so can we build a method that kind of adjusts this strategy flexibly, and we can specify different objectives as we go. And so this is an example. Let's say, in psychology, there's a very common model from psychology. It's called a psychometric function. It has a bunch of parameters like this lambda, gamma, alpha, beta, all the Greek letters. And you might care about some of them and not the others. Some of them might be quote unquote nuisance parameters, so you don't care about those, but you still need to infer them. But let's say, and depending on what you want to do, you might focus on learning one or the others. This is just to give you kind of a practical example of a situation which, as an experimenter, I've done some work in quantitative science, so I say you might care about some parameters than others. And this is telling you which ones. But let's say, so the idea is, okay, so we want to do all of these things, right? So we want to select the data to query. We want to do inference quickly based on what we acquired so far. And we also want to be able to kind of adjust and change on the fly what we are collecting. So what's the goal for, what's the things we care about? And unsurprisingly, wait, what if we try to put everything together? And nicely enough, let's say, of course, this might seem quite complex because, let's say, these are actually different goals, but say, remember, transformers have this really nice property that you can throw multiple things at them. And that's essentially how the idea for this project and this paper, ALINE, started, this Amortized Active Learning and INference Engine. And again, this was recently accepted at NeurIPS as a spotlight. And the idea is that then we can instantly, just again, just a forward pass, estimate posterior say posterior parameters, these latent variables, or predictive distributions, exactly like in ACE. But the same network can also be used to tell you which data points to acquire next in such a way that you get most information about what you care about. And what you care about, well, we can flag what we care about. You can imagine, you can really tick the boxes and say, okay, I care about this, this, and this. So I care about these parameters, or I care about this data. And then you say, and the network will adjust its behavior to collect as much information about whatever, whichever boxes you ticked. And it's very flexible in that way. And of course, there is a lot of work on related things. I don't know why this is still gray, but anyway, so there's been a lot of work on separate things, where say ALINE is the only one that does all of these things simultaneously. Right, so let's say, so kind of to tell you a bit about the framework and the setup. So we have these input-output pairs, x and y. Imagine again a function x with location x and value y, and parameters that govern this process or this function. And the idea is that we go on and collect data in iterations, in steps. So, and these go from 1 to big T. And we have a likelihood in the sense that given this information, so this given the parameters and the locations, we can predict through a model the values at these other points. And the idea from, again, imagine I have a function, and this may be modeled by a GP, or I have a cognitive model like the one I mentioned before. So let's say, so I can plug in the numbers and do the predictions if I have the model. And the idea is that then, given all these quantities, we can compute the posterior distribution, which is what you typically care about when you want to infer parameters. Or remember from before, we can also compute the posterior predictive, which is this given past observations and a bunch of query points, was the value at these points. Let's say this is a y star. And now, based on what we care about, whether it's posterior predictive, we might have different objectives. These are typical objective from Bayesian experimental design, which is, well, if you want to get information about the posterior, what you want to do is to maximize information gain about these parameters, these random variables theta. And, and it has a very traditional form, which, depends. So you want to minimize the entropy of the future posterior. So it can be written in many different ways. So this one way of writing it. And similarly, and they look different, but in some sense they're very similar at core, is that you can also, if you care about the posterior predictive, which is the ability of predicting future points, it is not quite the same as predicting the parameters of the model. These are two different objectives. So what you want to do is to essentially maximize the expected predictive information gain. So let's say, so again, how much information you gain about knowing these random variables, which is the value, for example, of your function at these query points. All right. Hope you're still on board. So if you have a small clarification question, feel free to ask them here. Otherwise, because I take big questions later. But I say exactly. So if you lost on minor things, I'm happy to clarify it along as I go. I forgot to mention it earlier. Okay. So as I mentioned before, we want to be flexible. This is somewhat, let's say, just a bookkeeping slide, but I just want to tell you, yes, we can essentially, we have a check mark that we can put on each one of our latent variables or our data points, and it is that I care about this. And this, it's called a target specifier, and then, there's a bunch of math just in terms of notation, but imagine really like, okay, here I say I care about, parameter 1 and 2, whatever parameter 1 and 2 are, and then, we can kind of tick them, and then the network knows that it needs to care about those 2 parameters, as opposed to, for example, caring for all of them, or no parameters, but only the data, and so on and so forth. So we can do all these these ticks. And so this works for both for parameters or for targets for our data. All right. So again, this is the problem setup. We want to jointly learn this amortized model that does all of these things that I mentioned. And specifically, so what it has, so you have your data that you embed. You have this big transformer, and we have this selective mask, which I mentioned, which essentially tell you what you care about. And then we do 2 things, because these are 2 separate things that the network does, but it's the same network, so just kind of just different heads. One is the policy head, which tells you, okay, given everything observed so far and what I care about, this is the design, this is the input you should query next, okay? And it just tells you which input to query next. The idea that, that you go to the real world, you query that input, you run that experiment, and then you put back the query and the results, the outcome of the experiment is y, back into the data, and then, you can go on querying points. At any point, as you go, or at the end, then you can do inference, given all the points seen so far, and their values. Let's infer either the parameters, for example, this distribution about one parameter of interest, or let's say the data, which can be, this function. And as you get more data, this becomes more informative. For example, your posterior becomes narrower, so let's say you're more sure about what the parameters that generate the data are, or you get more sure about the values or the function at different points. And then again, this depends which ones, let's say, becomes better. Well, depends on what you targeted. And again, so for example, what this will look like is that, as before, we have a context set. And also we have this query set, which is the points that we query for, say, doing our design, say, experimental design loop. And then we have our target, which is, what we at the end go on to infer. And this can be latent variables or actual data points. And the query, so the only difference is that the query sets live in the input space. So let's say, so we go and decide, which points to query. So you can see there are no latents here, but, we could extend it if it made sense. In this specific case, it doesn't make a lot of sense. And, and then say the architecture should be similar to what you saw before, just, even more stuff. So in the sense, we have the context set, we have the query set, which is a new thing, which essentially outputs through this acquisition head. It tells you which points gives you essentially a probability distribution over potential queries, and then you can sample from it, or you can take the max to decide which point to query next. And the inference head is very similar to what we saw before with ACE, in the sense that you give it some points, either the latents or the input points, and then it predicts the values to a distribution. It could be a Gaussian, it could be a mixture of Gaussians, it could be a Riemannian distribution at those points. Now, sorry, this, okay. How do we train the inference model? So the inference part is actually pretty easy to train because it does exactly like in ACE. So the idea is that we have a bunch of points that we've seen. Then, we have a bunch of points that we keep on the side, and we call them targets. They're like test points. And then let's say we just ask the network to predict those points given whatever we have observed so far. And this part doesn't care about, it doesn't care how you got those points, if these come from the acquisition or not. These are just points. So say it takes all these points that you observed, their values, is this is context, and then predicts at new points or at specific latents. Okay, so that's exactly like ACE. So nothing new, and we can just train this. Now the other big question is, okay, but how do you train the policy? Okay, and the cool part about essentially this project is that now you can start seeing why these two things make a lot of sense together, because we can actually train this through self-supervised reinforcement learning, in the sense that we can use the prediction from the inference head to guide learning for the policy head. Now, that's not strictly needed, but using that streamlines and makes this way smoother. And essentially, because again, the network has already learned good representations. It knows about the uncertainties about about different points. So effectively learning the policy on top of that becomes much easier. And essentially, we are rewarding the model for learning to predict better, to making its own prediction better. So there is math, which I don't have the time to cover. So I say, but essentially, so what we do is we can take these objectives from, say, classical experimental design, these expected information gain, or expected predictive information gain, and make it self-predictive, and where essentially we plug in instead of the ground truth here, we have our own approximate inference predictor. So this Q phi is the prediction from the inference heads. Now, this is still grounded in reality, because let's say what we do is we can do multiple predictions, multiple samples of designs, and then check how well we predict the targets which we care about, given the sequence of design we took. And let's say, so when doing training, we need to have the ground truth. So we use the ground truth doing training, but the point is, it becomes much smoother because we have access to this intermediate representation thanks to these inference heads. So the idea is that now we can, for example, before in traditional experimental design, people would use surrogate models like Gaussian processes to represent functions. And now we can just replace that with ALINE. We might still use Gaussian process doing training as examples of functions. We might use whatever examples we want. We can use other more complex models. But then at runtime, since ALINE essentially builds its own surrogate models. And then, for the acquisition function, which is, how do you select next points? Again, there are lots of choices in traditional experimental design. Here, we have our own policy, which again, let's say, it's chosen in such a way that, it can really use this self prediction. So essentially, it's a variant of EPIG or EIG, but let's say it exploits this internal prediction. And so how do we train it? We can train in many different ways. It is that you just need to have a lot of data to train on, and typically it is done by having a flexible simulator, which you can use to sample a lot of different examples of things you care about, like functions. For example, you can sample from Gaussian process priors, but more recently you could sample from structural causal modeling priors, which is are being popularized in the past few years by the success. And so you can use a lot of different priors you can sample from. And And then the idea is that then we can deploy them. So, and we evaluate. So I'm going to explain what's happening, which is very fast. So I expect I wait for the next round. But say the idea is that here is, we want to learn, this is active learning. So we're learning the shape of this function. And this is all ALINE, okay? So the underlying function is here in red. And the uncertainty and this all aligns predictions. So say this uncertainty comes from ALINE. And what it's doing is, again, it's following this policy, which is telling it to maximize information gain about the data. And as you can see, let's say what it's doing is quite intuitive in the sense that it's kind of going and, it's probably looking like they're doing uncertainty sampling, which is, kind of minimize the points with maximum uncertainty, if you look exactly what it's doing. So it's similar to that, but say we're not telling it to follow that specific. It's following this expected predicted information gain objective. And let's see if my computer is crashing. And then, we can, so that's just an example, we can compare it against a lot of other methods, some traditional ones using Gaussian processes. For example, we use these ACE, which I presented before, but let's say without only the inference part, so without having the policy head, just ACE, and then we just use some a simple uncertainty sampling policy. And ALINE essentially, as you can see, performs very well, and eventually performs best in all cases, or at least on par with best. And so yeah, this short take home, yes, it works. And but the other thing that we can do with ALINE, which we think is quite cool, is that you can change its objective. So for example, we take the same network that we had before, but now we say we don't care about learning the function itself. We want to learn the hyperparameters of the GP. In this case, would be, for example, the length scale, the output scale. And so let's say, so now we focus on that, and we can have essentially the same network focusing on that. And what's nice is that we see that then, at deployment, now changing the strategy at deployment, just telling it, no, we care about only the parameters, so not specific about the function per se. We can see that, yes, this is more informative than doing, other things. Which I think is nice. There are other examples here. Yet another example of source localization, which is kind of, we want to find where the source is. Again, it's very quick, so it kind of already found it. So you need to wait until the next round to see what happens. But these are the kind of design points. The star is the true source, and it starts saving a few points. Essentially, we want to, and what you see here, this shaded area, essentially are these the log probability of where the source is, and of course, it's found it. So, anyways, there are a bunch of kind of standard examples from experimental design. And then we apply it to this example from cognitive science. Again, there is this model that tells you how people respond to stimuli. It's kind of a universal model using a lot of different scenarios. It's called a psychometric function. Again, it has a bunch of different parameters. You may or may not care about some of them. And the point is that there are already existing state-of-the-art methods in cognitive science that kind of deploy looking for different parameters. And then we can see that ALINE essentially works like the state-of-the-art methods, but with the difference that we are amortized, the other methods are not amortized. So essentially, so again, you can get kind of this at runtime, which is actually useful because the point is when you run an experiment, so you often have a real person there doing the experiment. So you can't wait, a minute to get the next design. You want to get it, let's say, within a second, for example, so that you can keep running the experiment as you go and get the next, stimulus to show to your participant. All right. So I think let's say we're kind of wrapping up. So we think let's say this again kind of just the first step. Both ACE and ALINE are part of this kind of agenda that we have in my lab and also say in our collaborators' labs. That we see we can use this power of amortization and pre-training, and of course we're not the only people doing it, to really expand what we can do with probabilistic inference. And a lot of the things that were kind of theoretically nice but unachievable in the past because they were just computationally intractable or would take too long. Now we can use these networks, train the networks to solve these issues. And we think that there are a lot of things that we can do with that because, again, once we can scale to high dimensional tasks, larger contexts, so on and so forth, once we make these methods more robust, and that's an interesting open question, there is essentially, yeah, so the sky is the limit in the sense that we can actually apply them to a lot of usage cases. And of course, AutoML is an obviously interesting direction and application for us. So let's say, so this is not by chance that I'm talking to you now. And so I want to thank again my collaborators who really did the heavy lifting a lot. Let's say, so these are the people who collaborated for the ACE paper, and this one for, you can see there's some overlap, this one for the ALINE paper. And I don't know, actually, it's possible some of them are in the call at the moment. I don't see who's there. And yeah, this we have some, oops, sorry. Okay, now everything is stuck. But I think, let's say I'm done. So I want to just thank you again. Thanks, everybody. And yeah, happy to take questions.